Hello, today we're talking about power series. So a power series, we're going to look at how a power series of a function is represented in the derivatives of the function and the power series and how this all matches up. So of course it says we encounter this in section 12.1, which I'm not sure if we got that exploration done in class or not. So we're going to go ahead and do this. Find the first order through fourth order derivatives. So what that means is find the first derivative, second derivative, third derivative, and fourth derivative. This is most easily done by realizing, let's rewrite our function in calculus friendly terms, which is this, and we have to use the chain rule. Okay, so for the first derivative, that's going to be negative 6, 1 minus x raised to the negative 2 times a negative 1. That negative 1 is the derivative of the inside. So that's the same as a positive 6 times 1 minus x to the negative 2. So my next derivative, I'm actually going to write it out sort of not simplified first, and then we can simplify it if we would like to. So negative 2 times 6 times 1 minus x raised to the negative 2, and again the derivative of the inside is negative 1. So I'm just going to write that as a positive 2 times 6, 1 minus x raised to the negative 2. Sorry, that should be a negative 3. I apologize. I've already messed up my derivatives. My exponents, I didn't actually subtract 1. So that should be a negative 3 here and here. So moving on to the third derivative. So I'm going to take the derivative of that. So I bring my negative 3 down. So I have negative 3 times 2 times 6 times 1 minus x, now raise the negative fourth. I think I got that one right this time. And then, of course, I'm going to make that positive. So it's 3 times 2 times 6 times 1 minus x raised to the negative 4. And then we have our fourth derivative. So again, I bring my negative 4 down. Negative 4 times 3 times 2 times 6 times 1 minus x raised to the negative 4th times the derivative of the inside, which is a negative 1. And of course, my negative 1 makes it positive. So I have 4 times 3 times 2 times 6 times 1 minus x raised to the negative 5th. Sorry, I didn't change my exponent on the other one either. So fix my exponent. Right here should be negative 5. Okay, and there's a reason why I wrote it this way, and hopefully we will see why momentarily. So number 2 says, okay, go ahead and evaluate f of 0 and f prime of 0, f double prime of 0, f triple prime of 0, and f fourth prime of 0. So let me go back to f. F is up at the top, and I'm plugging in x is 0. So f of 0 is going to be 6 over 1, which is just 6. So let me fill that in right here. Actually, I don't want to use red. Okay, so f prime of 0. So I'm using my red derivative up above. That's my first derivative, and I'm going to plug in x is 0. So I have 6 times 1 raised to the negative 2, which is just 6. For my next evaluation, I'm taking the second derivative and plugging in 0. So I end up with 2 times 6. You can write that as 12 if it makes you feel better. The next one, the third derivative, plugging in 0, and again, I end up with a 1 raised to the negative 4th, but I end up with 3 times 2 times 6, and that gives me 36, if you would like to write it that way. And for the fourth derivative, I plug in 0. I have 1 raised to the negative 5th, and I have 4 times 3 times 2 times 6, and I believe that's 144. So next thing we're going to do is we're going to find the first 4 derivatives of p. Now, p was up at the top. Let's see if I can see both. Barely. Okay, so p is up at the top. I'm going to take that derivative. Okay, so I take that derivative, and the derivative of 6 is 0. The derivative of 6x is 6. The derivative of 6x squared is 2 times 6x. The next derivative is 3 times 6x squared. The next one is 4 times 6x cubed, etc. And I'll continue as I need to. Actually, I'm going to go ahead and write in this space and I'll erase it later. So plus 5 times 6x to the 4th. And of course this continues. So my next derivative, I'm going to scroll down a lot. My next derivative is going to just be 2 times 6 plus 2 times 3 times 6x plus 3 times 4 times 6x squared plus 4 times 5 times 6x cubed. My next derivative, 12 turns into a 0, so I start with 2 times 3 times 6 plus 2 times 3 times 4 times 6x plus 3 times 4 times 5 times 6x squared plus, and in my fourth derivative I have 2 times 3 times 4 times 6 plus 2 times 3 times 4 times 5 times 6x plus my other terms. So now I'm going to do the same thing I did with my function. I'm going to use my polynomial, my power series, and I'm going to evaluate p and the other derivatives at x is equal to 0. So I'm going to scroll back up so I can see my p. And when I can see my p, if I plug in 0 for x, because this pattern is going to continue, p of 0 is just going to be 6. So p of 0 is going to be 6. Now when I evaluate p prime of 0, because of this pattern continuing on, I'm also going to get 6. P double prime of 0, when I plug in a 0, I will get 2 times 12, which again, if it makes, 2 times 6, which again, if it makes you feel better, you can write as 12. My third derivative is going to be 2 times 3 times 6, which is going to be 36. And then my fourth derivative is going to be 2 times 3 times 4 times 6, which is 144. So number 5 says, well, what's the relationship between all of these f's and f primes and all these p and p primes, and the corresponding derivatives and functions at 0 are exactly the same. So what's our relationship here? They are the same. They're equal, whichever you want to write. Next, number 6. So f of x and p of x have the same value and the same slope at x equals 0. And the second derivative is the same as, the second derivative of f is the same as the second derivative of p. So they have the same rate of change of slope. And the third derivatives are equal, so the rate of change of the slope is the same. So that means the more derivatives of the two functions that are equal, the better these functions fit each other. So basically, the better the functions fit each other, to say it actually properly, the better the values of p fit the values of f. But we need to be a little bit more specific. It's not for everywhere. We've really only looked around x is equal to 0. So it's really only for values of x close to x equals 0. And if you need to pause that to finish writing, go ahead and pause that. Now for number 7, I'm going to erase what I have because I'm in my space. For number 7, we're going to find out that f and p are the same as long as we do the division. So for f was 6 divided by 1 minus x, and we're going to do division. I, of course, am going to do division with the boxes. You're welcome to do long division if you would like. You're welcome to do synthetic division you would like, as long as you know how to do it. So I'm going to divide 1 minus x. I'm going to divide that by 6. So I start filling in, and 6 times 1 is 6, and 6 times negative x is negative 6x. Now, when I take 6 and I divide by 1 minus x, I'm trying to figure out, okay, well, what am I going to end up with? But what I want to end up with is I don't want to have any x's. Sorry, I want to have a 6. I don't want to have any x's. So the next term would be a positive 6x because I want these guys to make a 0. So now I just have a 6 up here, which means down here I'm going to have a negative 6x. And again, divide however it is you'd like. Again, I don't want, sorry, this isn't 6x, I apologize. 6x goes up in the top so that I have a 6x below right here. And then this box becomes a 6x squared. But I don't want to have any 6x squareds. I want to have 0x squared, so I need to add a 6x squared, so I don't have any. And then I'm going to multiply by 6x squared, and that gives me negative 6x cubed. And I believe you can probably see the pattern that's going to continue. Add 6x cubed, and then I'm left with plus 6x cubed here. Down below I have negative 6x to the fourth. And I don't want to have any x to the fourth, so I add 6x to the fourth here, which gives me a 6x to the fourth, and down here a negative 6x to the fifth, which again, I would need to add 6x to the fifth, which gives me a 6x to the fifth, which gives me negative 6x to the sixth, and we can see that this pattern is going to continue. So when I take 6 and I divide by 1 minus x, I end up with 6 plus 6x plus 6x squared plus 6x cubed plus 6x to the fourth plus 6x to the fifth. Of course, that's the top. That's what I end up when I divide. So moving on to the next page, Exploration 12-4A. So we're also working with power series again, and a power series is going to match a function as best it can around a certain x value. And right here, number 1, we have the general Maclaurin series, and this is how it looks when we have any power series. It's going to be a constant plus some constant times x plus some constant times x squared, some constant x cubed, x to the fourth, x to the fifth, etc., continuing on infinitely. So what I'm going to do first is I'm going to write the first few derivatives. Now I'm going to write it in the notation that I did on the other handout. So I'm going to start by, this first derivative is c sub 1, the next one is 2c sub 2x, the next one is 3c sub 3x squared, plus 4c sub 4x cubed, plus 5c sub 4x to the fourth, plus 6 c sub 6 x to the fifth, and I see that I called c4 twice. Sorry, this c4 right here should really be a c to the fifth. So when I say I'm going to do it in the same manner, what I mean is I'm not going to multiply anything out. So my next derivative is just going to be 2 times c2. The next term would be 2 times 3 c3x. The next one is 3 times 4 c4 x squared. The next one is 4 times 5 c sub 5 x cubed. The next one is 5 times 6 c6 x to the fourth. And again, I hope that you can see that there is a pattern emerging out of here. Next derivative is just 2 times 3 c3. Next one is 2 times 3 times 4 c4x. Next is 3 times 4 times 5 c5x squared, and 4 times 5 times 6 c6x cubed. And of course, I apologize, I should have that these continue infinitely. I forgot to add that. Fourth derivative, I have 2 times 3 times 4 c4. I have 2 times 3 times 4 times 5 c5. I have 3 times 4 times 5 times 6 c6 x squared. I forgot my x over here with my c5. Dot, dot, dot. And then my fifth derivative is 2 times 3 times 4 times 5 c5 plus 2 times 3 times 4 times 5 times 6 c6x, and on and on and on. So number 2 says evaluate the function and each of the derivatives at x equals 0. And we're going to rewrite it using factorials. And as you can see, I've set it up so that we can see the factorials fairly easily. So p sub 0 is just called c sub 0, right? If I take p of x up top and I plug in x is 0, I'm going to get c sub 0. So that's just c sub 0. There's no factorial needed on that one. For the next one, I want the derivative now. So now I'm down at this one. The derivative, if I plug in x is 0, I get c sub 1. I am going to write that one as a factorial because 1 factorial is 1. And that's 1 factorial times c1. Now, p double prime at 0, I'm now on the blue. I'm going to get 2c2. And 2 is the same as 2 times 1, which is 2 factorial. So that's 2 factorial times c2. The next one, I'm in green now. I plug in 0 for x, and I get 2 times 3 times c3, and that is 3 factorial. So again, 3 factorial would be 3 times 2 times 1. And of course, we're not writing the times 1, but it really is there. Next one, I'm moving on to the black derivative, the fourth derivative. So that's going to be 2 times 3 times 4 c4, which is 4 factorial times c4. And then my fifth derivative, which again is in red, is 2 times 3 times 4 times 5 c5, which is 5 factorial c5. So hopefully you can see the relationship between the first derivative and the idea of what the first derivative at 0 is. First derivative is 1 factorial times the first constant, c sub 1. And the second derivative is 2 factorial times c sub 2, so on, so on, so on. So if we were going to write the kth derivative at 0 using factorials, that should be k factorial c sub k. So for number 3, what we're going to do is we're actually going to do this and see how it helps us. So, and again, what we need to remember is these are not the constants. The c naught, c1, the c2, the c3, etc. are the constants in our function, our power series. Okay, so it's not 2 factorial times c2 is what's in front of my x squared. I'm going to scroll up real fast. When I look at my c2 term, it's just c2 times x squared. Okay, it's just c2 times x squared. So why is that relevant? So let's look at this. I'm going to find out my derivatives first, and I'm going to do my evaluation. So I start with f of x is sine of x, so I take the derivative. That derivative is cosine of x. I take the derivative of that. That is negative sine of x. I take the derivative of that, and that is negative cosine of x. I take the derivative of that, and that is sine of x. I take the derivative of that, and it is cosine of x. So here are all my derivatives. Now I need to evaluate each one of these at 0. So sine of x at 0. Sine of 0, sorry, let me get my little sketches going. So here's my sine, 2 pi, pi, and then here's my cosine, 2 pi, pi. Okay, helps me out. So the sine at 0 is 0. Cosine at 0 is 1. Negative sine at 0 is 0. Negative cosine at 0 is negative 1. Sine of 0 is 0. And cosine of 0 is 1. So we have figured out that each of these are equal to the factorial times the constant. So let me show you what I mean. I'm going to scroll down just a little bit. So in the chart at the top, I know that p sub 0 is c0. So this right here is my c sub 0. In the next one, p prime of 0 is 1 factorial to 1 factorial times C1. So that tells me, the first line tells me C naught is 0, C sub 1 is 1. The next one, 0 should be equal to 2 factorial C sub 2, which means C sub 2 is still 0. The next one tells me that 3 factorial C3 is negative 1, which tells me what C3 is. C3 is equal to negative 1 over 3 factorial. And we're going to leave it just like that. This one, fourth derivative is equal to 4 factorial C4. That tells me C4 is 0. The next one is 5 factorial C5. That tells me that C sub 5 is equal to 1 over 5 factorial. And now with that knowledge, we should be able to write the P of x that's going to fit sine of x. So down here, we can write down all of our constants. C naught was 0, C1 is 1, C2 is 0, C3 is 1 over 3 factorial, C4 is 0, and C5 is 1 over 5 factorial. So now I'm going to write my terms. And when I write my terms, it's literally just, sorry, I'm going to kind of cross this out. My P of x is exactly as it's written above. And that is C naught plus C1x plus C2x squared plus C3x cubed plus C4x to the fourth, etc., etc., etc. So we're going to write sine of x. So sine of x is going to be C naught, which is 0, plus C1 times x to the first power, plus C2 x to the second power, plus C3 x to the third power. Wait, I missed a negative. I apologize. When I wrote down my C3 down here, I missed my negative. So this should be a negative right here. Sorry about that. Plus 0 x to the fourth, plus now I'm on my fifth, 1 over 5 factorial x to the fifth. If I had to guess, the next one, the derivative is going to be 0, so 0 x to the sixth. And if I had to guess, the next one would be 1 over 7 factorial x to the 7. This one would probably be negative because my signs seem to be alternating. What I mean is this is a positive, this one is a negative, this is a positive, so this should be a negative as well. Plus dot 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 continues on infinitely. And of course, if you wanted to simplify it, you could. We could just write it with the terms that aren't zeros. So sine of x should be approximately 1x, or just x, minus 1 over 3 factorial x cubed plus 1 over 5 factorial x to the fifth minus 1 over 7 factorial x to the 7. I could continue this on. And that's the whole point. It should be infinite, etc., etc., etc. So that's the basics of how you create a power series for any given function. So I apologize for the length of the video, but I hope you have a better understanding of this and a wonderful evening.